In this video, we'll talk about some miscellaneous tips and techniques that you can use to help speed up your code in Julia. We'll focus on the example that we introduced in the last video of optimizing a physics simulation. As a reminder, last time the performance of our simulation wasn't able to keep up with only 350 particles, and we instead averaged a frame rate of around 12 frames per second, and we had these intermittent lag spikes. By reducing the number of memory allocations, we were able to improve our simulation's performance and make the frame rate much more consistent. However, we still weren't able to achieve a full 60 frames per second. So in this video, let's try and fix that. So before we start optimizing, let's look at where we were last session. Before we started our optimization, we were at around 600 microseconds in the meantime, which is what we care about for our simulation. By reducing the allocations, we were able to get this down to around 200 microseconds instead. So this is around a 3 times jump in performance. Let's go into the code and see if we can make any improvements to make this performance difference much greater. In this session, we'll just focus on the acceleration fast function and see if we can make this as fast as possible because it's the limiting factor in our simulation. The first tip when optimizing code is to make sure you're not recalculating new results every time when they're not changing. If we look inside our doubly nested for loop, you can see that we're calculating this pi static vector every single round of the for loop. However, the contents here don't depend on the inner for loop. So instead of calculating this result here, we can move this up so that it's only calculated once at the beginning of the outer for loop. If we run the benchmark again, you can see that we went from around 170 microseconds now to only 150 microseconds. So this is only a small change, but it gives us a reasonable speed up. The second optimization I want to make is at the end of this for loop. You can see that we're adding into a vector which involves reading from the accelerations matrix and writing to that matrix. In one of our previous videos, we looked at the speed of different operations that a CPU can handle, and reading from memory is one of the slower operations that a CPU can perform. And so we want to optimize this function to make sure that we're only reading from main memory when we need to. Otherwise, we want to be dealing with things that are allocated on the stack and therefore are likely to be in the cache. So instead of adding to the acceleration matrix within the inner loop, instead we'll keep track of the total and write this result into the matrix only at the end of our inner for loop. To do this, we need to create another static vector which is initialized at 0. We'll then move this for loop at the bottom after the end for loop. And instead of adding the component for the inner loop, we'll instead add the entire vector. But this code is not correct without adding to our original variable, which we can do with this simple broadcast operation. One thing that's very important to know is because we're using static vectors, we can't perform this operation in place. Instead, we have to overwrite the original memory. But because we're allocating on the stack, this shouldn't hurt performance. One small thing that we should change is instead of adding to the initial vector, we can just set it equal to the component, since the result here will be the total acceleration felt by the particle I. But since we're overwriting this result, we no longer need to reset the input array, and we can remove this first line. So this is only a modest change, but it should make a reasonable impact on the performance. So now we can see that our performance is at around 140 microseconds. So this actually wasn't too large an impact compared to before, but it did make a small improvement. The next optimization will involve knowing how Julia indexes into an array. We'll hop into a REPL to see how this works and see what we can do to improve performance. So in Julia, if we have a matrix and we want to index one of the elements, for example, 1, 2. Whenever we want to index into an array, this operation won't run until Julia has checked whether 1, 2 is within the bounds of the array. We can see this if we try and index outside of the array. Julia will throw an error because it's performed a bounds check, and this bounds check can degrade the performance of your program. If we know that our algorithm is correct and it will always index into a correct set of bounds for our input, we can tell Julia to ignore bounds checking for the duration of a calculation. Let's see how this is done in our simulation code. Turning off bounds checking in Julia is actually quite easy. We can just use the inbounds macro, which will apply to any block of code following this expression. In this case, it will turn off bounds checking for the entire doubly nested for loop. This should affect all of the indexing operations within our for loop. If we actually benchmark this code, you can see that adding inbounds didn't actually affect performance too much. However, you might be able to find some examples of where you can improve performance by turning off bounds checking. So now we've got to the point where we've exhausted all of the easy optimization techniques. So now what we'll do is try and modify the algorithm so that it will run as fast as possible. Let's look at the actual operations that are occurring. In particular, let's focus on these two operations. In the first operation, we're calculating the force between two objects, and in the second operation, we're calculating the acceleration. However, when we're calculating the force, we multiply by the mass of object I, and in the second line, we take the result of this force and then divide out the mass of I. This means that this operation is superfluous. We don't need to multiply here, since we're just going to divide by it later on. What we can do is take the components of f that are actually needed and put them directly in our expression for the acceleration. The resulting expression gets rid of the superfluous memory access, and it also reduces the number of divisions, since we can combine dividing by r squared with dividing by r to give dividing by r cubed. Now when we run our benchmark again, we're down to only 78 microseconds. So this gave a roughly 2 times increase in performance just by changing 2 lines of code. Now we're at a point where the performance is likely good enough to run our simulation at 60 frames per second. So let's open up our simulation and see whether we've achieved our goal. So now we have our simulation, and if we click run, you can see we're at a smooth 60 frames per second. You can see that the optimizations we made here were able to increase the frame rate from around 45 frames per second to 60 frames per second. What this means is we can now increase the number of particles shown on screen and maintain the same 60 frames per second performance. So now that we've made this improvement, let's see if we can go even further. For our next optimization, let's get some inspiration from our original implementation using matrices. Let's use our original implementation to have a look at the forces between each particle in our simulation. So we'll take this code and some initial conditions and run it in the terminal. Once we've run our code, we'll get this force matrix. And you can see something quite interesting. This matrix is completely symmetrical. If you remember back to your early physics classes learning about Newton's laws of motion, you should remember that every force has an equal and opposite reaction. In this case, the force of attraction between these two particles is equal in magnitude, but opposite in direction. So once we've calculated the force on I with respect to j, we already know the force on j with respect to I, we just need to add a minus sign. What this means for our code is that we only actually need to calculate the lower triangle in our optimization, because the lower triangle will give you the upper triangle values that you need. So now that we know that there's an equal and opposite force, what we can do is use this to calculate the acceleration on body j with respect to I. So in order to properly do this, what we can do is copy the line and change this to j and swap the order of the indices. Finally, we need to add a minus sign on the front. So this is good, but we still have some redundant operations, and so we can extract these repeated operations into a single line above. Additionally, we can move the indexing operation to before the for loop because it doesn't depend on j. This technique is called hoisting. So now that we have this, let's change our implementation to directly write into the accelerations array. We can move the write operation back inside the for loop and remove our local AI variable. Now that we have the component for ji, we can directly add this into our matrix. We want to make sure that we're only using the lower triangle of our matrix, and in order to do this, we need to make sure that our inner loop doesn't repeat indices. So instead of going from 1 to n, this should go from I plus 1 to n. But now that we've written this code, we know that j will never be equal to I, and so we can get rid of our initial check. Before we run our benchmark, we need to also revert the initial change that resets our accelerations array equal to 0. Now we run our benchmark to make sure that our algorithm is correct and actually produces a performance increase. So you can see that our algorithm is now correct. However, we're getting a worse performance than before. This is why we need to be so careful when we're doing our benchmarking. Even though our new algorithm is technically more efficient, it didn't actually lead to any speedups, and in fact reduced the performance slightly. So let's see if we can try and remove this performance regression. One thing that I think is getting in the way of our performance here is we're messing with the cache locality of our read operations. So instead, I'll try to break up these two operations into 2 chunks. What we'll do is make sure we're only adding the j components inside the for loop, and then after the j for loop, we'll add up all of the components calculated within the for loop. To do this, we'll need to reintroduce our temporary variable and make sure it's keeping track of the total components within our for loop. If we run this benchmark a final time, you can see that we've gained a very small speed up. And before we run our simulation for a final time, let's see if we can squeeze out one more performance optimization. For the final part of this video, I want to show you how you can make your algorithm more generic while still being able to use packages like static arrays. Value types are very useful in Julia, and they allow you to give information to the compiler so that it can use that information to optimize your code further, while still letting you write generic code. If we switch back to our code for a second, you can see one clear problem with using the static arrays package. We were forced into hard coding the number of elements in the static array, so these elements could be efficiently allocated on the stack. But what we can do is inject the number of dimensions that we need to use into the type information for this function. Since arrays are dynamic in Julia, the size of the arrays aren't passed in with their type information. Instead, the only information included is the type of its elements and the number of dimensions that are used, and not their sizes. The way we can pass this information is through one of these value types. This means we need to edit the function signature to make sure that this information is accessible. So this new parameter will be dim, but we will specify that this should be a value type, and value types are always parametric. And the parameter that we pass into this type will be the data that we need to use. In this case, I'll call this type D, and since this is a generic parameter type, we need to add an extra statement to the end of our function signature to make sure that it's defined. The way we do this in Julia is with the where clause. This is a bit of a strange syntax, but the outside defines the parameter D, which can then be used within the type information for the arguments. But once we've defined this, we're free to use D within the code, and now D is just some compile time constant that we can pass into this function. And remember, Julia's multiple dispatch system will allow you to compile different versions of this function depending on the value of D. But now that we have this information, you will notice this blue squiggly line underneath our first line of our function. And this says invalid redefinition of a constant. And so this gives us a clue that D is now a constant within our code, and so we don't actually need to take it in here. What I can do is rename this to DA for the dimensionality of our array. And then we can always add this assert statement to make sure that this is true, and if the statement is false, then the function will throw an error to force users into inputting arrays of the right size. In this example though, I'm going to remove the assert statement, and we'll just assume that our users will call this function correctly. Unfortunately, we can't just change this to D and hope everything works. Unfortunately, the way that the svector macro is defined means the range is evaluated at pass time, and D is not a constant that's available globally. So what we have to do is use a slightly different constructor. Fortunately, the changes to this are quite simple. Instead of using the macro, we can use the svector constructor directly, and we can pass it a generator, which has the same structure as a list comprehension. We can repeat this throughout our code to make it more generic. So we've made all our changes to the acceleration fast function, but you'll notice that dim is still grayed out, and that's because we don't actually access the instance that stores this type information. And that's because val types are very special. They contain no runtime data, and the only data that it holds is within the type, and so we don't actually need to give this variable a name. We can just specify the type signature instead. One small change that we have to make to the acceleration fast function in order to use this svector syntax is to inject some type information into the constructor. The way that we do this is by adding curly brackets around the svector expression and then passing in the D type, and so this injects the size information directly into the type of the svector. We can also optionally specify that this should be float64, however this parameter can be inferred by the input type. If you didn't want to use this directly, what you could do first is create a tuple and then pass in the tuple into the svector constructor, and you'd have an expression that looks like this. However, I think it's cleaner just to change the type directly. And so we'll make the updates for all of these static arrays, and then we'll continue on to modify the rest of our code to use this value type. Since we changed the function signature for our acceleration fast function, we need to make sure that this change is propagated out to all the functions that call this function. You can easily spot this by looking at the blue underlines for each of our function calls, which is highlighted because we're not passing in the right number of arguments to our functions. And since we want this function to be compiled as well, we need to make sure that we pass in the type information into this function as well. So here I'm not going to specify the type, I'm just going to specify this parameter and then forward it into our acceleration fast function calls. So now that we've changed the signature here, we should go up to where we're using this in our test benchmark and finally pass in this value type. And the way that we construct this instance type is actually quite simple. First, we have to extract the number of dimensions that we're working with. And then secondly, we have to construct this val type. And now we can easily pass in this variable into both of our function calls. If you run this benchmark again, you can see an increase in performance. So not only were we able to make our code more generic, but we were also able to increase the performance. But you may be wondering, why was the performance improved here? And the key lies in how much information we were able to give the compiler. For now, let's just focus on this for loop. When the compiler generated this code, it knew that there were a fixed number of iterations, in this case only 3. So instead of writing machine code which directly performed this loop, instead it can just replace the function body with calls to this code 3 times. And these 3 statements will execute much quicker because there are no jump commands involved and the machine doesn't have to check any of the conditional statements. This is a common optimization done by compilers and it's called loop unrolling. For us this is really great because it means that we don't have to unroll the loop manually and instead we can write this generic code while also also providing the type information necessary for the compiler to be able to make these optimizations on its own. So up until now, we were able to make our code around 9 times faster by making all of these optimizations progressively. But I think we can go even further, but in order to do so, we need the help of another library. This package is called LoopVectorization, and it provides a very useful macro that we can use to optimize our code. This macro is the @turbo macro, which is very similar to the @simd macro that we looked at in previous lectures, except this macro is quite sophisticated and will automatically produce vectorized code, and by vectorization we mean using the simd instructions that are native to our hardware. In order to use this package, you need to make sure that you add it into your environment first. You also need to make sure that you import it at the top of your file. Now for some of your optimization problems, you might be able to just add @turbo on the front of your for loop. However, if we do this in this case and we try to include our code, you'll see an error pops up straight away. Unfortunately, this error doesn't have a lot of information, but I'll show you the changes that you need to do to make sure that your code can compile. Loop vectorization is designed to play quite nicely with static vectors. The only problem is it expects a certain syntax, and it hasn't yet been updated to use this generator syntax. For now, I'll remove this generator syntax, and instead hardcode the expression. Secondly, the @turbo macro doesn't work on nested for loops that aren't rectangular, and what we mean by rectangular is that the number of times the inner for loops execute shouldn't depend on the outer for loop. In this case, since most of our work is actually happening within this inner for loop, we can simply move the @turbo macro to before this for loop. What we also have to do is remove the type information passed into this S vector. And this is because the @turbo macro expects S vectors to follow only a narrow set of the syntaxes that are available. If we try and include this code again, you can see that now line 82 has a few issues, and so we can't use the anonymous syntax for defining a function. Fortunately, this is pretty easy to fix, and we can just define a function out here called square. So now we're able to actually include our code, but there still might be some issues with our code. So let's run our test benchmark function to see whether there are any errors. You'll notice that we have this error, a_ji is not defined in main. Now this is quite a confusing error, and it shows that the @turbo macro is not perfect in being able to convert our code. We can actually fix this quite easily by copying and pasting our AI vector and calling it a_ji instead. This makes sure that this variable exists before the turbo macro is called. Immediately when we're running our benchmark, you can see that some checks failed. For now, we'll just turn this warning off. So now that we've disabled this check, let's see if @turbo has done its work by running our benchmark for a final time. So now we have our benchmark results. We can see that we've had a massive speed up over the mean time to execute our update function for our physics simulation. Overall, we've seen around a 20 times speed up, and this is really quite a good speed up because we didn't actually change the algorithm that was being used, we just changed how we wrote the code. So now let's go back to our physics simulation and see what this improvement has allowed us to achieve. So now with our updated code, when we run our simulation with 550 particles, this runs at a smooth 60 frames per second. But in order for us to actually see these performance improvements, let's now instead remove the cap on the frame rate being 60 frames per second and see how many frames we're able to generate. So now without the frame rate being capped, you can see that we're now achieving around 155 frames per second. And remember, this is with 550 bodies. And let's compare this to our original implementation. You can see that in our original implementation, our performance graph goes off the charts. And in general, we're averaging around 4 or 5 frames per second. And this simulation is in fact completely unusable. If we're just looking at frames per second, our old implementation settled at around 3 frames per second, whereas our original implementation had around 150 frames per second. This means that our new code was around 50 times faster on average than our old code. This now means that we have much more overhead to run larger and larger simulations. In fact, let's try and push the simulation to 1,000 particles to see whether it can keep up. So now you can see with 1,000 particles we run around 48 frames per second, but this is still a very usable simulation. One thing that I want you to get out of this video is realizing that optimization can not only help speed up the code that you're currently running, but it also allows you to push your code further and solve larger and larger problems in the same amount of time as it would have taken you to solve the smaller problems. The main thing to say here is that optimization is a process that takes time. You have to try many different avenues to make sure that you're actually improving. But the main thing in this process that is constant is testing. You want to make sure that all of the optimizations that you're adding actually improve the performance of your code for the specific example that you care about. And the only way to be sure of that is to perform accurate benchmarking. If some of you are interested in optimizing this code, I've put it on GitHub to let you download it and have a go at optimizing it yourself. But I think I'll leave it there for this video. We'll pick up this example again next week when we start talking about parallel programming.